In this lesson, we'll be introduced to the Q equation, through which we can calculate the amount of thermal energy absorbed or released in a reaction. We can also use this equation to calculate the mass and change in temperature if the other variables are known. So remember, this Q is the amount of heat energy in joules released, M is mass in grams, C is that specific heat. You can put a little SP right there. Let me actually add that, SP, for specific heat, not just heat capacity. And then delta T is a change in temperature. In the last lesson, we used the specific heat equation C equals Q over M delta over delta T. So let me write that one for the last one. Remember, C of specific heat is equal to, it was Q over M and then delta T. Sorry that my delta looks like a P there. Let me take that out. All right, delta T. There we go. So in order to change, this is actually the same equation. These is just the same equation rearranged. So actually I'm going to show you how I'm going to do that. All I have to do is, you see these m delta t on the denominator, you just have to multiply both sides by m delta t. So we'll do times m delta t, and this side times m delta t. Not enough space there, so then this crosses out, and you just get q equals mCSP and then delta T. So just mass times specific heat times delta T. So we can use this reaction to solve for the amount of thermal energy in a reaction. We're going to go through an example of this real quick to see how to calculate the number of joules given off. So let me actually erase this over here so I can get some more space. Alright, so this example says calculate the number of joules given off when 32 grams of steam cools from 110 degrees Celsius to negative 40 degrees Celsius. So basically cools into ice. So remember, the specific heat of water, or H2O, which steam is H2O, is 4.184 joules per gram Celsius. Again, this can also be Kelvin, because again, all that matters is the change in temperature, and the difference between the Celsius and Kelvin will be the same. So let's start off by writing what we know and what we don't know. So what we're trying to find is the number of joules given off. So our Q is what we don't know. And then we have our M. Remember, the equation was Q equals mCSP and then delta T. You can also just call it C. But I'm just making sure you remember it's the specific heat. Q is what we're trying to find. The M, the mass, is equal to 32 grams. And then we have the CSP, we know that is the specific heat of water is always going to be 4.184 joule per gram Celsius. And I'm going to write let me bring it down a bit. And the change in temperature is from negative 40 to, let's see, so delta T, you go from 110 to negative 40. So your final is negative 40, and you guys subtract your initial, which is minus 110, and that ends up being negative 40 minus 110 is going to be negative 150 degrees Celsius. That's a change. So now let's add all this to the equation. So we have our Q, which is what we're trying to find, is equal to 32 times 4.184 times negative 150. So just take out a calculator, and we get, let's plug this in, we got 32 times 4.184 times, and this is going to be negative 150, but I'm going to put 150 in here and just change that to negative. So it's going to be negative 20,083.2. So it's going to be negative 20,083.2. And that is going to be, remember, Q is always going to be in joules, because this was joule per gram Celsius, and then the gram, the Celsius multiplied, so that goes away. And so your answer is just going to be in joules. If we made this into kilojoules, it'll be 20.083 kilojoules. So you might be a little confused on why the negative is there for heat energy, since heat energy is not usually considered a negative concept. But in this case, all we're considering is the flow of heat. So in this case, heat, it's not that we lost it, just got transferred somewhere else. So that's why it's negative. And this, since the temperature is reducing by negative 150 degrees Celsius, that means that it's an endothermic reaction. So the heat energy is absorbed. So we can also change the equation to solve for other variables. For example, like let's say, let me take this equation over here and rewrite it. So let's say, this time I'll use red. So we have, remember, it's Q equals mc delta T. Remember, that's SP right there. Remember, we already know if we want to calculate the specific heat, we just have to do Q divided by M times delta T. But if you want to find the others, let's say you want to find M. If you want to find M right here, you just have to make sure M is by itself. So the way you do that is you just divide C, the specific heat, and delta T from both sides. And so what you end up getting is, so let's divide both sides by C delta T, divide by C delta T, and so this crosses out, and so we get our M is equal to Q over C delta T. And same thing, if you want to solve for delta T, it's just you divide the MC instead. So let me write that over here, Q equals MC delta T. And we want to get delta T on it by itself, so we divide both sides by MC. And so we get, this crosses out, and so our delta T is equal to Q over MC. And remember, C, you can put the SP there for specific heat. So we're going to move on and do an example that is trying to find a variable other than heat energy. So this one says a certain mass of water was heated with 41,840 joules, raising its temperature from 22 degrees Celsius to 28.5 degrees Celsius. Calculate the mass. So what we know here is we're trying to find the M. We know our joules, our energy Q is 41,840, and we know our delta T. And if you remember, the specific heat of water is always going to be the same. From last lesson, it was 4.184 joules per gram Celsius. So let me write out everything we know here. So remember the equation we're going to use. I'm going to put it right here. It's going to be Q equals mc delta T. So in this case, let's write out what we know. So Q in this case is 41,840 joules. In this case, we don't know M, so we're going to put a little question mark for M. And then we know the C of water, CSP, is 4.184 joules per gram Celsius. And then the temperature, delta T, the change in temperature, we went from 22 degrees Celsius to 28.5 degrees Celsius. So to find the delta T, we got to take the final, which is 28.5, minus initial, which is 22. We got 28.5 minus 22. And if you do that, 20.5 minus 22 is going to be 6.5 degrees Celsius. So using that, we're going to change this equation up a bit. So we know it's Q equals mc delta T. Whoops. So let's make some room right here. I'll actually bring this out a bit so we can see everything. All right. So with this Q equals mc delta T, remember we want to solve for mass. So the way we do that is we divide both sides by C delta T by C delta T. And so what we get is this M is equal to Q over C delta T. So now we can just plug it into the equation. We know our Q, let's write this here, is equal to 41,840 joules. I'm going to use the units this time. And we know our C is 4.184 joules per gram Celsius. So let's write that 4.184 joules per gram Celsius. And then we have times 6.5 Celsius. So in this case, we know the Celsius and Celsius will cross out, and this joule and joule, since they're being divided, will also cross out. So then we're only left with grams. So let's take out this calculator right here. So the way you can do it, the easiest way is just put 41,840 divided, and then now we can put this in parentheses because this stuff is in the denominator, so it needs to be done first. So it's 4.184 times 6.5. I'm going to close that parentheses. And then remember, you still got to press equal again, so you get the final, which is, it's going to be equal to 1,538.4615. We can round that at 0.462. So it's going to be 1,538.462 grams. So it's only about 1.5 kilograms if you convert it to kilograms.